So now we're going to talk about the standard normal distribution. This is a really important section for us, so please pay close attention. So we've talked previously about discrete distributions. Well, now let's look at some properties about continuous distributions, because that's what the normal distribution is. It's a continuous distribution. The first thing I need to tell you about a continuous distribution is that you can't possibly list all of the values that the random variable could take on, because there's infinitely many of them. So we can't have a list like we did with the discrete random variable. With the continuous ones, we either use a formula or a graph. And every graph corresponds to a formula, but sometimes we look at it in one format or the other. So the next thing I need to tell you about continuous distributions is that because there are infinitely many possible values the random variable could take on, the probability that it is exactly equal to any one particular one of those values is practically zero. It's like the probability that if I left a grain of sand somewhere on a beach and asked you to go pick one up, that you go pick up a grain of sand and pick up the same one that I left. So that probability is practically zero. So for continuous distributions, we don't really talk about probabilities that the random variable equals a specific value. We look instead at intervals. So like we might want to find the probability that the random variable is between -1 and 1. In other words, what proportion of the time is it between -1 and 1? Okay, so that's continuous distributions in general. So now let's talk about the normal distribution. The normal distribution is very important for us for a couple of reasons. A lot of things in the real world follow a normal distribution. Not everything does. Not everything should. But that's one reason. The main reason for us, though, is that it's used as the basis for statistical inference. So it's kind of, I don't want to say behind the scenes, because it's really not behind the scenes. It's just there as the basis for a lot of what we do. So let's look at some properties of normal curves. So there are actually many, many different normal distributions. All of them follow the same shape. They're all this shape here: symmetric, unimodal, bell-shaped. There is a formula that goes with that, but it's a really messy formula. It's defined by mu and sigma. Mu is this value here in the middle where the peak is, and sigma determines how spread out it is. So normal curves are defined, again, by mu and sigma. Different mu, different sigma, different normal curve. Mu can be any value, negative, positive, or 0, and sigma can be any value as long as it's greater than 0. Okay, so that's normal curves in general. Now let's look at the standard normal distribution. So the standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. That's what makes it the standard normal distribution. So this is very important. The standard normal distribution is the normal distribution with mu of 0 and sigma of 1. For that particular normal distribution, that's called the standard normal distribution, and it's so important that it gets special notation. It's a z. Okay, the other ones are called x's. This one is z. So anytime you see Z, you know it's the standard normal. So the standard normal looks like this. Zero's in the middle, and we usually sketch Z values going out from -3 to 3 because most of the curve is included there from -3 to 3. But the Z values can go on from -infinity out to +infinity. But we just usually only look at -3 to 3 because that's where most of the values are. So the total area under the curve is 1. And what that means is there is a correspondence between area and probability. So if you look at the probability, for example, that Z is greater than 0, that's going to be half of the area. So that probability is going to be 0.5. So there's a lot of different ways you can find normal probabilities. But I want to use StatCrunch because we have that tool, and it's so much easier than any other of the options. So let's look at this first example. So if I want to find the probability that Z is between -1 and 1, and again, keep in mind, less than Z, less than 1 is the same as less than or equal to for these discrete, or for the continuous distributions. Alright, so I've pulled up StatCrunch, and on StatCrunch, if you go to Stat, Calculators, Normal, this will come up. So what we wanted here was the probability between -1 and 1. So we need to pick between, so that it'll give us two values here. And here this is already set up to do -1 and 1. So if you just type -1 here and 1 here, make sure your mean and standard deviation are 0 and 1. Hit compute. It tells us that this area is 0.6827. It also gives us the sketch, which is really nice too. So this tells us that the probability that Z is between -1 and 1 is 0.6827. And that's what the answer should be. Okay? And I put instructions here so you have it. Alright, so let's try another one. Probability Z less than -2.85. So now we don't need between. What we want is the standard, because that gives you just the one direction. We wanted the probability that Z was less than, so pick the less than, -2.85. So if you type -2.85 in, hit compute, it shows us that this area here is really small, as we would expect it to be, and the probability is 0.0022 if you round it to 4 decimal places. Alright? So 0.0022. Alright, so that probability Z less than -2.85 is 0.0022. Okay? So let's find another one. The probability that Z is greater than -1.24. Go back here. Now we want greater than, so we'll change the less than to greater than. I said -1.24. So we'll just type that in, hit compute, and we get 0.8925. Alright, and again it gives us the sketch. Alright, so that's all there is to finding the probabilities.